So, how you guys doing today? Doing good? Okay, perfect. So, how was your spring break? It's good? Perfect. So, here's what I'm going to do today. I'm going to review what we did slightly over before spring break, and then I will move on to the next subject. Sounds good, right? So, let's try to recall some of the things we did before. Okay? So, here's the thing that I want you to remember. This is the benzene here, okay? And then you're gonna treat this one with the methyl chloride, okay? Or the aluminum chloride catalyst over here. So if you do that here, what happened to this one? Okay? We're adding substitution of this one here, so you can have substitution happens over here. Okay? So this is one thing we learned before. Okay? So we have another one we do with the bromines. Here with also the iron 3 bromide. So in here, because of the substitution effect, do you guys remember this? Either you're going to have this the bromine group, bromo groups substitution, or either happen to ortho and para. You guys remember this, right? Okay. So then you're going to have this one. Okay. Or you could have this one. You see this here. Okay. So and then if you have the further treating with the nitric acid here, okay, with the sulfuric acid here. So you have adding nitric group here, but here's the thing. If you look at this one over here, this is going to be either these two substitute group effects. Can you guys guess which position this nitric group will be there? So if you guys remember the trend, also will be given. You don't have to memorize. This is stronger than this one. So the hydrogen groups in the somewhere in the middle. There's the electron donating groups is on the right. The other electron withdrawing groups on the left. So it means this is stronger. So they will actually have a position this nitric group either here or here. This also could this one here. This is it's also para directing. But because of this one is a stronger substituting group effect on this aromatic structure, we'll have this position because of this one is stronger than this one, so it will be this one. Okay, so this is the last one that we did on the chapter 16. Exactly the same problem will be on the exam. Okay, so once again, just copy this and memorize this one for the exam too. Okay, so this is the quite good summary that we did our last part of the chapter 16. So it's a kind of quick review. Okay, makes sense, right? This is a quick review. So just try to memorize this one. Okay? This will be on the exactly the same thing will be on the exam too. All right, so the before spring break, we talked about the alcohol and the phenol. So we know about the aromatic compound, and now we have a alcohol compound looks like this, right? So once again, if you have any hydroxy group on your like R, you can say alkyl part of your compound. This will become alcohol. This has become alcohol again. But as we know, have the benzene ring or all that conjugated aromatic compounds that also has the hydroxy group over here. You can say it's phenol. So this is type of way we just name this one as this is the phenol groups on here with the hydroxy group. So just the phenol right here, which is just the benzene ring with the hydrox group. We just named it that way. Okay? So once again, if you have this type of form in your part of the compounds, this will tell you about the double bond, which you have E and E form. You guys remember this, right? E and E. And then whenever we have hydrogen group, as you know, we have O and L. So that makes enol. So if you have this part of the compounds, becomes another type of alcohol. So regular one, phenol, and enol. So, all right. Makes sense, right? So if you have a certain type of direction over here, you can do it with some high temperature with the zinc oxide and some chromina catalyst. You're going to have methanol here. Here. You could also do with the ethylene. With the water and some phosphoric acid here. And some at high temperature. Okay. And then you can have ethanol here. Okay. So this is quite common already previous in human history. This is where we can prepare for some alcohol compounds easily from those materials. So we're actually going to learn how common those are already in the nature too. There is also we have this one obviously is quite common. Once again, this is phenol. This is usually in the coal tar. Okay, so you can assume this is very common in the plant. This is why, in a long time ago, not now I guess, but the scientists kind of expected that finding a lot of this phenol here in this coal tar, kind of proposing a lot of the trees died and buried in the ground amidst the coal. Maybe not anymore, but means this is quite common in the plant. That was the source of the information there. And then we also have salicylate. So this is quite common too, also in the plants, like in oil form. So this is also quite common natural product we see in the nature. As you can see, this part, where we can say this benzene ring portion is very common in nature as well. So we can always expect this one in the nature too. There's a funny one here. You guys know the poison ivy, right? Poison ivy. So this is the one that causes allergenic reactions to your body. So this is called urushiol. So this is with like a 2 hydrox group here on your benzene ring-like structure with some alkyl substituent groups over here. It's normally about 15 carbon long. The only difference on this R is either they're going to have a certain position where you can define the double bonds. So either it will be just all single bond all the way to single carbon 15 alkyl groups, while some usually some carbon 7 and 9 and 10 and 11. But this is whatever this R group here with this type of compound will cause some allergenic response here, especially on your skin. So this is something you can find in the poison ivy. So it's indeed for sure we have quite a lot of this in nature with this more phenotype of compounds rather than regular alcohol. Actually, it kind of makes sense though, right? If you think about the not just alcohol, but with the just very well conjugated ring structure, like benzene, benzo, or phenyl groups, will make those compounds much more in a stable form. Okay, so that is kind of why we see a lot of this in the nature too. Okay, so the all right, so let's try to do the nomenclature again. Whenever we try to name the alcohol, first thing I just want you to know this one. So before we get into the nomenclature, I just want you to know this is a primary alcohol. It's because the only one R group over there. Okay. If there is a 2, obviously this will become secondary, right? Secondary alcohol. If you have a 3 R groups on it, that makes the tertiary alcohol. Okay, so this is quite makes sense, right? So this is one thing before we move on to the nomenclature. Okay, real quick, 1, 2, 3. Okay, yeah. All right, so let's do the nomenclature here. So if you have this one, if you have this one over here, and then you have this group and this group here. Okay, so you have this type of compounds here. So it's actually pretty much the same. You just need to find the longest carbon chain. Okay, longest carbon chain, which will be 6 carbons there. So this is right. Okay, 6 carbons. So 1, 2, 3, 4, 5, 6. Okay, so this is hexane. Okay, but because of this, the hydrox group, it makes what? Hexanol. Because you have to put the OL, it's indicating you have a hydrox group somewhere. So whenever you do that, you also need to locate that one over here, which is your primary job. Because if you think about, I don't know if it's good comparison here. Either you do this one, you're going to have a 1 methyl group, 1 hydrox group over there. Obviously, this is where you're going to have some characteristic of the compounds that will do a lot of chemical reaction with this hydrox group rather than just a methyl group, relatively speaking. So importance of this one is bigger than this one. So we always wanted to give the lowest possible number for location for your groups. That is more important, which is hydrox group over here. So this is why I'm going to count the carbon from here, not here. Okay. So if there was nothing here, you should count the carbon from here, right? So you can have a lowest possible local number for this methyl group here, right? Makes sense, right? But because of this hydroxyl group, which is more important, I'm going to count the carbon from here. Makes sense, right? So it'll be 2 hexane. Okay. So if that is the case, that makes 1, 2, 3, 4, 5. So 5 methyl, 2 hexane. Okay. Makes sense, right? Okay. Because the hydrox group is more important. So I'm not going to do 2 methyl, maybe 5 hexanol. Because of the alcohol, your hydrox group is more important. I'm going to count the carbon from right to the left. Okay. So if that is the case, there's one more thing I just want you to know is that if you have this nomenclature, that's okay too. This is kind of less confusing because you're putting this location of your hydrox group right before your alcohol name, OL. So 5-methyl-hexane 2-ol is okay too. So this is quite a newer way. It's new name, new nomenclature. This is kind of old way, but I don't mind at all. Okay, so either you can do this. This is kind of better because you can actually tell where the hydroxy group right there. But if you put it here, you're just like, oh, maybe some. But just in case, both are okay. Okay, makes sense, right? Okay. All right. All right. So if you have this one. So try to find your base first, which is this one, right? So I'm gonna write the cyclohexane because you have 6 carbons in the ring structure. So I'm gonna write the cyclohexane, okay, there. And then obviously you have 2 hydroxy group over here. So in this case, we're gonna do diol, okay, diol. Because there are 2 hydroxy group there, so we put di there, which means 2. So that makes cyclohexane diol. Okay, and then you just need to locate them, which is your way. If you can either count this one here or here, it could be 1, 2, 3, 4, 1, 2, 3, 4. So you can say 1 and 4 cyclohexane diol over here. There's one more thing that I kind of want you to remember. This is a ring structure, right? This is a ring structure, so you cannot rotate on the certain side. So in that way, make sure there's the hydroxy group heading in the same side based on the ring structure. So that is going to be cis 1,4 cyclohexane diol. Okay. So if you can think about the one we previously did, what you can also did is what? Cis cyclohexane 1,4 diol as well. That's okay too. Makes sense, right? So you put this one in here, right before your diol. So that makes the same name too. Makes sense, right? Okay. So if I put this one, okay, so maybe if I put this one in the wrong here, okay, it could have been what? Trans. Okay, trans. All right, let's move on. All right, let's try to do. Over here. Okay, so here what you can do is pretty much the same. You just need to find the longest carbon chain, which has 4 carbons in it. So it'd be butane, and you have a hydroxy group over there in your base, right? So it's a butanol. Okay. And then this is on. So here's the thing. It's pretty much the same. That I'm gonna count this one is more important groups than your phenyl groups over here. So I'm gonna count the carbon from here, like this. Not 1, 2, 3, 4, but 1, 2, 3, 4. So I can give the number 2 for this one, 3 for this one, because I think this is more important. Okay, so that makes the 2 butanol, and there's a 3 phenyl groups, 2 butanol. And then it's the same here. Butan 2-ol is also okay. It's also okay. Doesn't matter. All right. So makes sense, right? Can I move on? Oh, makes okay. All right. There's some tricky one over here. So this one is kind of funny because you have a very short alkyl group with the hydroxy group here, which is your methanol, right? Okay. So you can actually see this one as a additional group, the substituent group on your base, which is very short. So you can have phenyl methanol over here. Okay? But the another thing you can do is this is the new groups. Okay? This is phenyl group. That's why we put the phenyl group on this methanol. It's phenyl methanol here. But if you have one carbon with that phenyl group, and this one is we call benzyl group. Benzyl group. Okay. So this is the same as so if you actually count this one as your base instead of phenyl groups, include that carbon here into your base, they'll become benzyl alcohol. So this is kind of tricky one, but this is how you what group that you're putting on your name. Okay, so it's kind of tricky one, I guess, but that's the okay. All right, see. Does it make sense? Okay. Next one was the okay. Okay. If you have this one over here, let's try to make it. Okay. So here's the thing. Whenever you do the nomenclature, once again, finding the longest carbon chain is the most important thing. Okay. It's over here. Okay. So this will be 1, 2, 3, 4, 5. Okay. So now you guys know why I'm counting carbon from here, right? Because of this hydroxy group over here. Okay. So even though this is where you have a double bond over here, which you still need to count. This hydroxy group is more important here, right? So this is why I'm going to count the carbon from here, not here. So if we had just no hydroxy group over there, obviously we have to count the carbon from here because of the double bond. But because of the higher importance of the hydroxy group over than this double bond location, so I'm going to count the carbon. So that makes the 1, 2, 3, 4, and 5 over here. Okay. So that makes the 1, 2, 3, 4, 5, right? So this is pentene, because it's a double bond, where you have double bond between carbon 4 and 5, not 1 and 2. Okay. So this will be 4 pentene, and this is where you have okay. Okay, just a few more and we're done. Okay. Makes sense, right? Okay. All right, so in this case, you have this one as your base over here. Okay, so this is your base. So we'll use the phenol as your base, and then you just need to have this, the prefix, your substituent group over here on your base, which is methyl. And you can say either 1, 2, 3. So it'd be 3 methyl. Phenol is okay. You can also say what? Meta. Methyl phenol. It should be the same thing, right? This is a meta position to your phenol, which you have a hydroxy group. And then maybe can you guys try this one? So if you guys remember this, so you have this is also kind of what we did before in chapter 16. Can you guys maybe name this one? Okay, 1 minute. We can try this one together. Okay, maybe 10 seconds. Okay, so you see your base over here, right? So what's the answer? It would be 2 and 4, right? So 2,4 dinitrophenol. Makes sense, right? So once you get the way you have a base, this it's eased out from there. Okay? So that's pretty much. Okay. All right. So the now we're gonna talk about the characteristic of this alcohol or phenols, why they're so important over here. So if you have this type of alcohol over here, you're going to have the groups. Write it this way. Okay. You have okay, so if you have this type of this way. So if you have this type of can you guys remember this one? This is our hydrogen bond here. So if you have some alcohol or phenol, that will give us possibly some quite strong dipole interaction. We named it hydrogen bond. So this is the reason why if you have a propanol here, okay, and then you have butane, and you have what's that? Okay, chloroethane over here. So those are I'm not going to do all the calculation for you, but they all have a similar molecular weight. Okay? So you can double check with how many, there's 2 hydrogen, 3 hydrogen, they have to count the elements for the implied hydrogen. But they all have like 65, 60, 58 molecular weight on those 3 compounds, meaning molecular-wise, they should have a similar boiling points. Right? Because if it's heavier, it will have a very high boiling points. If it's lighter, you should have only a small amount of energy going in to make them in the gaseous phase, so it'll be very low boiling point. But since they have a similar boiling points, the molecular weight, they should have a similar boiling point as well. But the thing is, this one has the highest, which is 97. This is degree. This is really low, like almost 0 Celsius degree. This is about 12.5. So obviously you can see how strong the dipole intermolecular force they share with this type of alcohol compounds. That makes the one of the good characteristic of the alcohol or phenol, any compound that has a hydroxy group. Okay, so there's a couple of things I want to talk about. Is those can work as the weak base. This can work as weak base. So if you have some compounds with the hydrogen, maybe it can be water, most likely water, but it can be just grabbed as the proton there. Okay? So they become. So this is kind of the same as accepting the protons. As we know at the Bronsted-Lowry definition, it kind of works as base, but the this one is not strong. Oh, not strong. Okay? Because the this one happens easily. Okay? So that's why that makes this is a kind of like a weak base over here, and then they can also interestingly can work as a weak acid by just donating this hydrogen on your hydroxy group over here. So maybe they can just bond to the water, and then you can have this weird. So you have this goes on the top of the oxygen here, right? It becomes the negative charge oxygen without the proton bound to this one. We call this icoxide. Oops. Icoxide ion. Okay, so this is definitely can work as the weak acid as well. So this is kind of a good characteristic of the alcohol compounds. Because of this hydroxy group, they have a way to do some chemical reactions with this groups over here. So this is why it's so important over here. But the thing is, for example, the alcohol compound behave like a weak acid. Yeah. So since this is a weak acid here, the one thing you need to think about is the Ka. You guys remember this one, right, from Zinc 2? This will actually tell you how strong the acid your compound is. Okay, so this will give you we can say so this is Zinc 2. So if you put this, so if you have a very high Ka, okay, if you have very high Ka. Meaning you have a lots of numbers of this one and this one dissociate from your original compound, which in this case is alcohol, right? So meaning if you have a really high number Ka, meaning it's stronger, it behaves like a stronger acid there. Okay, makes sense, right? So, but this is kind of tricky one. But if Ka is higher, that means a stronger acid here, because you have a more higher dissociation from the compound that will give it more numbers of hydrogen cation or the proton, you can say. Then what we normally use instead of Ka is pKa, which is a negative log. So this is a negative log of Ka. So this is the one part I also gonna emphasize again. So this is a negative log, so lower pKa means a stronger acid. So it's a kind of the other way. So because of the higher Ka is a stronger acid, you have more protons coming out. But because this p-value is a negative log, meaning a lower number is actually stronger acid. Okay. It's good also reminder from the, I think, Olga 1 and Zinc 2. Okay. You guys remember this actually? You guys remember this? Okay. All right, so if that is the case, there's a certain case we can use this information here. Not all the alcohol show you the same acidity, meaning same number for pK value. So for example, if you have methanol over here, or you can have very bulky like a top butyl alcohol. Okay. So if you look at these two over here, the pKa value for this one is 15.45. This is about 18. So which one is stronger? Tell me. The left one, for sure. So this is much stronger, right? So the reason why this is stronger acid here. I mean still the pK value is not so low actually. So you can actually say it's actually still very weak acid here. But relatively speaking, this is stronger because of the way they. So if you think about the alkoxide ion form of this one and this one. So if you look at once they donate the protons, okay, and this will become, I'm just gonna write it this way, is okay? Is okay? Because I don't wanna, so then this is the, okay, you see that, right? So if you look at this one in the solution, meaning this is becoming your solute, and you're going to have a lot of molecule, which is a solvent, right? So if they dissolve in the solvent, the small numbers of something dissolve in a lot bigger, abundant molecule, meaning it's solvation, because meaning like they're dissolving into the solvent molecules. If you think about that way, because of this bulky groups that leaving only one oxygen on the very limited space with the negative charge, it won't be easily solvated, meaning it won't be easily dissolved. Okay, but this one it only has one side that has one methyl group, but this side is very open to the larger numbers of the solvent molecules. So this will be much easily dissolved. Okay, so that means what? If that can be more easily dissolved, that have a more interaction, more room for them to be what? Dissociate the hydrogen. So they can be more slightly, relatively speaking, stronger acid there than this one, which is a much extreme case of the bulkiness on this side of the hydroxy group, but here it's very less. Okay? So that makes this one better or stronger acid than the other one. Kind of makes sense? Okay. So another one you can think of is the induction. We have okay. So oh, this is the last one today. So if you have this one, so once again, pK for butyl alcohol is 18. This is actually quite low. This is about 5.4. So this is a negative log form, right? This is a negative log. So even like the gap between these two is extremely different, because it's in the logarithmic expression over here. So this makes a lot more stronger than butyl alcohol over here. So this is what we call the inductive effect or induction, you can say. So this is pretty much because of this fluoride groups on this carbon that makes very strong attractive force onto the electrons on this part over here. That makes this oxygen here in the hydroxy group much stronger to pulling the electrons. So if you look at the closer look on here, it will be easier for this oxygen if we have a stronger force to attract those electrons share in the covalent bond between these two. That makes the easier for them to detach the proton away. That makes the stronger acid. Because the help from the not neighboring carbon, but even further from the fluoro groups that gets very strong electronegative elements that pulling electron density turn to the bottom. That help this oxygen to steal these electrons share in the previously in the covalent bond onto their oxide form, alkoxide form, then it's easier for them to leave the hydrogen here, which is stronger. Because stronger means simply they're donating more numbers of protons, which would be this. Okay. But not so much over here, which is even tougher. That's so big. Some effect, inductively not so helpful. Kind of makes sense. Okay. So this is why you're going to have some different types of the alcohol or phenol compounds that shows the different pKa, sometimes very extremely different because of that. But still, they won't be so strong, except a very few cases, but that's pretty much. All right, so let me stop here today.